IAG seminar series, and today it is my great pleasure to introduce Ivan Almeida. So Ivan is visiting us from. Okay, so Ivan is visiting us this week. So he's staying in room D311, and Ivan is one example of he is a prime example of a success case of our former students. Ivan, he did his PhD here, so he did his bachelor's in physics here in USP, and then he did his PhD here at IAG under my supervision, and he studied in his PhD accretion physics around black holes and the production of outflows and winds and how they impact their galaxies. And after his PhD, Ivan was disputed by many universities and institutes, got many offers for his first postdoc, and he decided to go to Newcastle University, or should I say Newcastle? Newcastle University, where he was working on the topics that he will present to us today. So topics, AGN feedback, the impact of supermassive black holes on their host galaxies, simulations of these processes. And then he's doing his second postdoc, and again, he was disputed by many universities, as he was telling me. And he decided to go to, so he's now working in the Max Planck Institute for Astronomy in Heidelberg, working in jet physics from supermassive black holes, high energy emission from these jets, doing numerical simulations of such processes. So Ivan, it's our great pleasure to have you here. Welcome back. Yeah. And let's hear from Ivan. Thank you, Ivan.
Well, thank you very much, Rodrigo, for the very kind words. Well, as Rodrigo said, I did my master's and PhD here at the IAG, and it's kind of nostalgic to see this place again. And I'm very happy to be here, to be sharing my work right now. So, well, let's start. First, just to situate everyone here. Well, as you all know, in the center of each giant galaxy, there is a supermassive black hole. This black hole has masses larger than 10 to 5 solar masses. Their sizes go beyond 1 astronomical unit for the very large ones. But I want to point out that for me at least, the most interesting thing about them is that when these supermassive black holes start to accrete the gas at the surroundings, they become active. They become what we call active galactic nuclei, and this is the most powerful, most bright, the brightest even that we can observe in the universe. The luminosity of this object can reach 10 to 47 ergs per second. They can outshine the host galaxy, so they are very interesting objects in the universe. And one very important thing about AGN is that this is the famous M-sigma relation, where we have the supermassive black hole mass plotted against the velocity dispersion of the host galaxy, and we can see this very interesting relation that shows us that the supermassive black hole, which is very small compared to the galaxy, it's in the scale of some microparsec of size, they are co-evolving with the galaxy. They have this very linear, this is a power law of course, but this is very direct relation. So these supermassive black holes, they evolve together with the galaxy, and they are a very important ingredient to understand galaxy evolution also, because these objects going here. Oops, let's come back a little bit. Here is illustration from the very nice review from Harrison and Almeida from last year, where they discuss AGN feedback. AGN feedback is this interplay between the AGN, the supermassive black hole, and the host galaxy, where we have a relation. The galaxy feed the black hole will produce some outflows, will create an energetic output that will affect the galaxy, and then we have a cycle of these two things. One important thing about, important thing about AGN feedback is that we are talking about a phenomena that starts, where's my pointer? That starts at the black hole scales, which is at this very, very small scale of microparsec. And then this black hole will accrete material. This material will form an accretion disk around the black hole. This accretion disk has a subparsec, in a superparsec scale, and this system will produce a lot of outflows. Some very powerful energy ejections arise from this system. Here we have this is just an artistic representation of the accretion disk. We have the black hole at the center, and while a lot of material falls into the black hole, they spiral and fall to the black hole. Some process will drive away powerful winds. These winds can be magnetically driven or radiatively driven, and also we can launch some powerful jets. So a large amount of the energy that we can imagine that will fall to the black hole are actually ejected, and this energy is comparable to the gravitational binding energy of the galaxy. So essentially this system here, in theory, could explode the galaxy, blow away everything. And this is incredible if you look to the scales we're talking about. So for this systems, while they are accreting material, they accrete in different ways, okay, depending on certain parameters, especially what we call the Eddington ratio. The Eddington, here we can measure the luminosity or the accretion rate, mass accretion rate of this system as a fraction of the Eddington ratios. That the Eddington luminosity is defined by, if you have a gas that you can at certain, where's here the point. Okay, if you have a particle of the gas that is falling to the black hole, it's attracted by the gravity, but if during the accretion process we can release a lot of radiation, and if the luminosity equals to the Eddington luminosity, it means that the radiation pressure balances the gravitational fall. This force is that's not exactly a force, but in the Newtonian sense, we have this balance between the two forces. Depending on this parameter, especially the mass accretion rate, we have different accretion flows around the supermassive black hole. For very low accretion rates, we have what we call, for values below this 1% of the Eddington ratio, we have some radiatively inefficient accretion flows, which are composed by a thick disk, and these systems do not produce a lot of radiation. They have a very small radiative efficiency. This value is just the ratio between the accreted energy, the rest mass energy, compared to the ejected radiation, how much they radiate. So this system radiates small amount of things, and they have this thick geometry, and they are very prone to produce relativistic jets, for example. If, as we approach the unity, here we have a different accretion flow, have the thin disk. This disk is present a high radiative efficiency, and they are more related to quasars and also cipher. And if we go beyond 1, which is the extreme scenario where we produce tons of radiation, we come back to the thick disk, but this disk is completely different from this one. They have some similarities, but here the disk is inflated by radiation pressure, because this is producing a huge amount of radiation. Super Eddington accretion is let's say less common and can be important at certain points of the AGN history. Coming back to this nice plot, we can see here that we started here at the black hole. We know that it produces a lot of outflows. These outflows will go to the galaxy, but comparing the scales, microparsec, milliparsec, and the galaxy is on this 1 kiloparsec to 10 kiloparsec. We have a huge amount of scales here. The outflows will interact with this region, the torus region, also the circumnuclear disk region. They will also interact in the region that we call narrow line region, the extended narrow line region, and they can go even further beyond the galaxy and interacting with the circumgalactic medium, and also if in a cluster, the intercluster medium. So here we have a phenomena that spans for more than 10 orders of magnitude. This is a real challenge for us to fully understand phenomena, because we cannot just model everything at once, and we can't simulate from the black hole to the cluster size. And also, if we look into the content of the galaxy, of the ISM, of the CGM, the ICM, we have a very complex medium that has atomic and molecular gas. We have this warm ionized gas also. So in terms of temperature, the AGN feedback interacts with gas that spans over more than 7, 8 orders of magnitude in temperature and density. Plus, we have also in the middle, this mass, we also have dust, have stars doing things. So the complete understanding of how AGN can impact the galaxy and impact the universe, it's a gigantic task. Okay, so just here another image from the same review. We have this nice flowchart showing that everything starts at the black hole mass, and then we have this AGN event when the black hole starts to accrete. The AGN will produce. The AGN produce outflows, which means that they are injecting energy into the galaxy, and as the AGN inject energy, they change properties of the galaxy, and this changes the way the galaxy feeds the black hole. So we have a self-regulation process here. And AGN are also an episodic event. So most of the time the black hole is not active, but when it's active, we start this cycle. So the AGN will eject energy, and this energy can have here in this plot they divide in 2 main categories: the AGN feedback effects. The first is this localized and transient, which is, for example, if we have some gas here, some cold gas, the AGN outflows will interact immediately and just destroy it. So this is the negative feedback, because as we destroy this cool gas, we prevent, for example, star formation. At the same time, if we have this gas, the AGN can produce a shock that will compress the gas, increasing the density and increasing the star formation rate. This is positive feedback. We have these 2 things that can happen, and this is some kind of for a theorist, we don't know exactly how to balance this, what's dominate depending on scenario, things like this. And also we have some global and long-term effects created by the continuous injection of energy of the AGN into the medium, which will change, for example, the size of the galaxies, the way the gas is distributed. For example, in cosmological simulations, we need to take into account the effect of AGN to reproduce the sizes and the properties, the simulated galaxies that match the observed ones. And also, in the long term, we expect that the AGN will suppress star formation, because essentially we are heating the gas of the galaxy, and as we heat, it will prevent the collapse that will form stars. So we have now a big picture of the AGN feedback. So let's come back to this plot here. Now we'll talk about what is my target, what I'm interested in. My target is essentially how this supermassive black hole can impact the host galaxy. I'm interested in the impact on the multiphase ISM. Okay, so I'm working on these scales. I'm not go further. I'm not working with the like megaparsec jet or something like this. I'm more interested in the effect in the single galaxy. So this is I think the biggest question that are driving my work. First, what are the mechanisms behind the AGN feedback, and how this AGN outflows can impact the ISM. For this, now I'm starting presenting some of my projects and my work. I divided this presentation in 3 parts. Project 1, I will talk about the interaction of a quasar wind into this multiphase ISM, and how this AGN can impact especially the gas with temperatures below 20,000 Kelvin, which is a warm ionized phase. I'll also talk about this project. These 2 are ongoing. I'll talk about this project that I'm trying to bridge the scales from the GRMHD simulations, from the vicinity of the black hole to the galaxy, and understand how the jet can impact the ISM. And this 3rd project, I've just talk a little bit because I just started. This is my current work on my new job. This project started 2 months ago. I'll just give you an introduction of what I'm planning to do. So let's start with project 1. Project 1 is coming back to this very useful image. This project is located at this part of the diagram. I'm trying to look the host galaxy. For this, just saying, I'm a simulator. I work with numerical simulations. And for this project, I'm using this code, a REPL. A REPL is a massively parallel code for gravitational and body systems and MHD, both on Newtonian and cosmological backgrounds. A REPL this is the official release. This is the code developed mainly by Weinberg and Springel, Pachmo. Springel has worked in this for decades, this code. Oops, come back. Here I'm just showing some different applications of a REPL. Here you have a simulation, a cosmological simulation a REPL can do. The work from Marinacci. Here in Costa 20, we have a simulation of a single galaxy interacting with a quasar wind. You can see this multiphase is the galaxy, and then we have this very large bubbles produced by the quasar winds. And also we have an implementation of a jet simulation using a REPL. So a REPL is very well suited to AGN simulations. Okay. Here for this simulation, I'm using a REPL plus the module BOLA. BOLA means boundary outflow layer for AGN. It's developed by Thiago Costa. I work with him in Newcastle University. This module is essentially, we have a REPL. A REPL have this grid that following the Voronoi mesh. Okay, and we set at some point of my numerical domain. We fixed the numerical cells in a way that I'm forming a sphere, or at least something that looks like a sphere. So the mesh is regular. Once these cells are fixed, I can control the fluxes that goes from this region, which means I have for example, a galaxy, I can set a region of 1 parsec, for example, and inject mass, energy, magnetic field, inject gas certain velocity, which means this will be, for my model, the AGN zone, and I'm just plugging to the galaxy the energetic output of the AGN, and then I'll see what happened to the galaxy. So for this project, we are trying to understand the impact of the AGN into the multiphased ISM. So we need to define what is our ISM. We are using the model developed by Samuel Ward. He was a PhD student in Newcastle. Now he's a postdoc at CCA. He did an amazing job implementing the simulations. Samuel model, consider we have the smooth disk, which I think is not the most interesting case, just a homogeneous medium. And we find a way to create a clump medium that has a constant mass and match the expected density and temperature values for the ISM, for the clumpy ISM. He explored different clump size just to check if it changes, what changed the structure of the ISM. This is an artificial ISM, but this is what we can model for now. Okay, and also we use different agent power, not just from 10 to 42. Okay, for this model, for these simulations are hydro. I'm planning to expand them to magnetohydrodynamics. This temperature range for 10 to 3 to 10 to 9 Kelvin. Densities goes up to 10 to 4 centimeter cube. This model considering primordial cooling of hydrogen and helium. For the next step, I'm also planning to do metaline cooling for this model. And right now we have Huda. Huda is a PhD student at Newcastle University, and she's also doing an amazing job implementing dust physics for this model. We'll soon ready. And this is the edge-on view of a density map of this clumpy ISM. And if we plug, for example, a jet here, we can have interaction or a quasar wind also. So I'm showing here some simulations of Samuel. This is, I should play, okay. Samuel implemented using Bola, and that the initial condition I mentioned, and they have a spherical wind. And here we have density, the velocity, the wind density. There is a tracer, tracing the AGN wind, and pressure. And you can see here this galaxy, and the AGN just blow everything away. You have clearly the AGN is doing something to the galaxy. Okay, so they're changing the properties of the gas. For this simulation, the AGN zone, the Bola, is 10 parsec region, which is very small compared to the galaxy. So one interesting thing that Samuel found in his simulations is if we have an AGN simulation without cooling and with cooling, we have different outflows. Okay? So cooling is very important for this phenomena. If we have no cooling, we have some kind of a smooth outflow. As we add cooling, we start to see this very small cloudlet that goes away with the AGN. This cloudlet has on the parsec scale. Okay, so we have this interesting difference. And one thing that I'm interested in is understanding how this cloudlet can survive to the outflow and how they be important for observations and so on. So this is my simulation. What I'm doing is focusing on this small cloudlet, this I will call warm-cool phase, which is it's a material with temperatures below 20,000 Kelvin. Here I'm showing 3 different simulations in the same panel. One for a 10 to 43 ergs per second AGN, another one with 10 to 45, and the very nice one with 10 to 47. we have a mass resolution for this cells as 100 solar masses for the base resolution, and we increase resolution for the outflowing cool gas to something around 2 solar masses. This is very high resolution for this type of simulation. We have a boost compared here by a factor of 64 times. When I say outflowing cool gas, I'm referring gas with temperature below 20,000 Kelvin, Mach number greater than 1, and they have this mass greater than the density times this cooling length, which is essentially the fragmentation scale of the gas. What does it mean? I am refining more cells that can fragment because of the cooling. As the cell cool, imagine we have a large cloud and they will start to cool down. The cooling will create denser regions. They have created a lot of many denser regions and fragment the original cloud. This scale is just the fragmentation scale of the system. What I'm saying is that
this is thermal energy injection.
This is kinetic energy injection. Yeah, thank you, Rodrigo. Okay, so here I'm showing another 3 simulations at different AGN powers, 10 to 44 to 10 to 46. In this green-blue is density, and the reddish one, the red-pink, is pressure. We increase the resolution on these clouds, and we study how these structures are formed, and we found that they are even smaller than SEMO found. They can be below 1 parsec. It's just a zoom in of 100 parsec. We have many cloudlets going on, and these clouds are moving along the AGN outflow. If we look into this different AGN powers, 10 to 44 to 10 to 46, we will increase the wind connect power. We can see that all these inset plots on the same scale. We can see that these cool structures are just decreasing in size and become denser. The density difference is not very easy to see, but the size is very clear. We are creating smaller and denser clouds as we increase the AGN power. So, first thing that we found for this work is that brighter AGN produce denser, cool, warm outflows. Here we have a cloud. This is the largest cloud that we have in the 10 to 45 simulation, plus a lot of very small ones. Here we have the structure, and here I'm showing the distribution of the density. Okay, I'm sorry, I erased the density values here, but the peak is around 10 to 3 centimeters per cube. And if we can say, but maybe these clouds are similar to the initial condition. Here is the initial cool gas distribution, our initial SM. So we can see that the AGN compressed this gas and create a very interesting log normal distribution of density for the clouds, which is in agreement with a lot of cloud crushing experiments that have many works in the literature. Okay, here we have these clouds. We can check the density distribution as function of the AGN power. Again, we can see the shift on density. For 10 to 43, we have much less dense clouds compared to higher power. For this analysis, I need to define what is a cloud, which is not a trivial. We define these clouds as any structure that has velocity above 10 kilometers per second, which is this threshold here guarantee that is the movement of these clouds are because of the AGN and not some kind of diffusion thing of the gas of the galaxy. I'm looking for this temperature, this phase, and a cloud should be larger than 100 cells in a numerical domain, just to avoid any noisy. One thing that I forgot to mention about the initial condition is that the velocity is 0 for everything. So anything that's moving in a simulation with velocities higher than 10 kilometers per second is due to the AGN. We choose this because we want to isolate anything that's not AGN from the effect. So this is our choice to do zero velocity initial condition. We also have different ISM models. We have one ISM with small clumps, large clumps, medium clumps, which is our fiducial model, and we also check it if we change the wind velocity as we injected it, how it will change the characteristics of this phase, and we found that the ISM, of course, this result depends on the ISM, but it's a moderate effect. Okay, it's not drastic as the AGN power. So if, for example, you look to the result that you found for different AGN power, and that's but maybe this is related to the size of the clumps from my initial condition. We tested this, and the effect is due to the AGN. The effect for changing initial conditions not drastic as changing AGN power. Here's the biggest result that we got. We have this cool gas clouds and plotting the density. Where's the point? Have the density, and it increased with AGN following relation of the AGN to the square root, to square root of the AGN power. So we have this power law, which is kind of not expected as we start the simulation. And again, we can see the decrease on size of this clouds following this power law. But here the scatter is much bigger. Anyway, this power law can be related to this one, just if we considering size and volume relation. So again, the main result for this is the AGN, this phase reacts to the AGN in a power law following this rule here. We can also imagine if this is something related to the way I selected clouds, and then I'm plotting here the density as function of AGN power for different phases. We have here for temperature below 20,000 Kelvin, here for higher than 20,000 Kelvin, and here for the very hot gas. And I'm not using here any selection criteria, just picking the cells on the simulation and taking the average. And again, we have the same relation with the square root for this cool phase, while this hotter phase and the very hot gas follows a more linear relation. Except for this point here, we'll have a break. But this simulation 10 to 47 is a special one in the sense that the AGN is too powerful and just destroy everything. So we have a kind of break at some point here. The AGN start to be more destructive to everything. This relation to L to square root can be explained by a sum of two things. First is related to how the gas cools, because we need cooling to have the structures. So when we have a mixing between the hot phase, the hot wind plus initial cold gas, we will get a phase with a temperature that is the geometrical average, which is just from this will arrive the square root relation that we are observing. Okay, now let's go to some observational implications that may be more interesting for some of you. For this, I'm working with Chris Harrison. He's an observer, my previous boss in Newcastle University, and he has helped me a lot on discuss how this can be interesting for observers. here I'm showing usually we calculate mass outflow rates and the kinetic energy that's flowing from these outflows using this formula here. Just is the total mass of the outflow, and this value comes from several emission lines. Okay. The point here is from our simulations we can calculate easily the outflow rate because we know what's going on, and we can here showing the cumulative ratio. If we look to here, we have 1 centimeter per cube. It means that I'm looking to the fraction of the outflow of the flowing material that has density above this. So here I have 100%. We go to higher numbers, for example, at 100, for example, we have for 10 to 43 eggs per second, have like 40% of the outflow of the outflowing material has density above 100 centimeter per cube, but it's almost 100% for 10 to 47. So, and if you look also for the kinetic coupling, for in the same way, if we look for very dense gas, for example, some lines trace gas at density of 1,000 centimeters per cube, and if we look for this line and try to infer the kinetic coupling, we will get a much smaller value or something like this. Our results showing that the mass of flow rate increase with the AGN power, which is kind of expected, considering the cool gas, and the energy coupling decreases, which is not as what we see in simulations. For example, here it's hard to say that the AGN has less impact for the 10 to 47 than compared to the 10 to 43, because the AGN is just blowing away. The point here is, depending on the line that we are looking at, maybe we are not seeing the complete picture. Here we have our result that the density depends on the AGN power, and here we have some observational data from Fiore 17 and Bischetti 19. They relate the m dot. They calculated the outflow rate for different AGNs and have this relation here, but they used a fixed value for density, and our results showing that we cannot consider it's the same density for the ionized phase. These observations are of ionized gas. Okay, all 3 lines like this, and they consider it a fixed density. Our results show that we cannot use this fixed density. We need to measure the density actually to properly infer the m dot, and then with the relation we found, we propose a correction by so this is the original relation that used in some works, but we've taken into account that the density change with AGN power, we will get a much smooth relation for m dot for the outflow rate. I read this. So, and here, just comparing our result with observations. Here we have this is the electron density measured using different methods. For yellow, these are observational points. Okay, the points, the yellow are measuring. They are measuring with sulfur 2. For the white ones, they are using transauroral lines, and this brown region, they are using this ionization parameter method. I think they are using O3. Well, oops. We have very a huge scatter here. If we try this whole sample and do some tests, we'll find there is a slight increase, and here is our results for the cool phase, the warm cool phase. We have this line here. If you look only for the very dense gas, you have this line from our simulations, and if you take just the maximum density of our clouds, have here. So our simulations are somehow comprised of these results. But one important thing is that, for example, is that there are some objects that are measured on SUFO2. They are also measured transauroral lines and O3. The same object, they have different densities. So they're essentially tracking different phases. And if you want to estimate the outflow properties, we need to have to measure several lines and have much more all the information that we can get, of course. So, but yeah, this is kind of hard. Well, for this, I'm planning to publish this work very soon, hopefully next week. For a next step of this work is trying to implement meta-line cooling and properly estimate some emission lines to compare with the observations. Thiago is also developing some radiative transfer for a ripple, and this is the next step for this particular project. Maybe I take too much time on this project. I'll just try to be faster for project 2, which is something that I presented last week on the conference in Rio. So here, oops, okay, all right. The project 2, we start here with GRMHD simulations of the accretion disk. I'm interested in systems that produce relativist jets and the regime of 10 to minus 2, 10 to minus 3 of the Eddington ratio. For this, we expect the black hole to be accreting to the accretion flow of this relativist black hole is a geometrically thick accretion disk, optically thin, an extremely hot disk, and that has extremely low relative efficiency, RIFE. This model is supported by a lot of observations of AGN, especially in the local universe. For example, the IAG-USP are using this model to model M87, for example. For this project, I'm using, for the GR part, simulating nearby to the black hole, I'm using HAMR. HAMR is a massively scalable GPU accelerated general relativistic magnetohydrodynamics code. It's based on HARM. This is a very used GRMHD code. HAMR solves the MHD equations under a fixed metric. In our case, KER, black hole metric. And we have plenty of very nice videos on YouTube, on Liska YouTube, if you want to check some nice simulations of tilted accretion disks and so on. Liska is the main developer of HAMR. Here we have a GRMHD simulation using HAMR. We started with a Fishbone-Moncrief accretion disk. For this simulation, I am working with Pedro Mota, who's a PhD student here, which is helping me a lot of details of the code. Here I have some parameters for the simulations. We have a box of 10 to 4 RG, which is something like 10 to. This is 3D simulation. 3D. This is some milliparsec scale for 10 to 8 black hole mass, 10 to 8 solar mass black hole. We aim to run for 50,000 RG over C time, which is this gravitational time, which is around for 1 year. Let's say this is small scale, and also the time is kind of small for astronomical implications. For this simulation, we have a maximum spin black hole, 0.9375, and a magnetization parameter of 100. Yeah. This is a 5 region one, so yeah. It's 3D, but for this plot, it's 5 region. So because of this, symmetric because of this. You have here for the simulation, we have 3 main regions. We have here this input cone dominated by magnetic energy. We have the jet. Here the equator, the very dense region. We have the inflow region, the accretion disk itself that's feeding the black hole, and here in the diagonal we have the ejection of some hot magnetically driven winds, much slower than the jet, but it can carry away a considerable amount of energy and mass from this system. So the idea for I am more interested actually for nowadays I'm more interested in the interaction of the AGN outflow with the ISM. So I'm using these simulations to create a model that I can inject into my galaxy. So we have here have the black hole. This is just a scheme. This will produce a wind plus a jet. I will set up a sphere around the black hole, and I calculate the fluxes for magnetic flux, the mass outflow, the mass flux, the energy flux that are crossing this surface. Also to measure the velocity of the fluid. I want to create this function f that depends on the position and also the spin of the black hole. If I can explore the spin of the black hole, the magnetization parameter. I can calculate this function to use on the large-scale simulation of the galaxy. So I plan to run several simulations of this. As I have ready on this one, but I'm having it's on the queue of the computer for spin equal to 1/2, and also with smaller beta values. Here we have will be a bit quicker. Have the mass outflow rate following this power law. I'm just calculating the integrated over all angles as a function of r. But if I look at different parts, different angular regions, I track different components of this outflow. I can track the jet or the winds. Sometimes I just look at the inflow region. So we have it's depending on the angle. This the mass outflow rate depends on angle and the distance to the black hole. So here we have a radial profile and okay, we have the radial profile and the angular profile that I need both to my future implementation. For the energy outflow rate, I do the same because I need the mass energy. I also do this analysis for velocity, magnetic flux. I'm using this, creating this profile, calculating this profile from the GRMHD simulation to feed into my galaxy simulation. So I have this part of the project that I talked here, and I want to simulate this zone, which is much larger one. I of course have I have a gap here between the boundary radius and my between actually the radius that I can the convergence radius for my simulations here, which is around 300 RG, 300 of this gravitational radius. You can think as half of the Schwarzschild radius in size. To the boundary radius, that is the injection region. Have this region where to bridge this gap, I will do some assumptions. I have this power laws. I assume that will stand up to the boundary radius, and also I need to add some mass to the jet, this input jet, considering that we have eventual particle creation and some kind of mass loading. So I will need to be very quick now. I will use Bola again, equal to the first project. I just pick this profiles. These are my input parameters. This is the function, of course, I'll just implement these functions in a condition for my boundary for galaxy. For my galaxy, and this is an example of a jet simulation. This is an extreme case of a 10 to 45 jet power for this galaxy. But we can see how, and also we have this different angles for the jet possible, and here we can see the jet interacting with the ISM. They also produce some of these clouds that I talked in the previous project, and depending on the angle, we have more spherical outflow. Here, for example, this jet is comprised in the galaxy. It's not escaping. If I have a perpendicular jet, the interaction with the galaxy is much smaller, and we have that more traditional jet image. I will just be very quick on the project tree, but I think it's fine because I started 2 months ago, so I don't have a lot of things, a lot of results yet. The third project is located here at the 10 parsec scale. I am trying to understand how jets can accelerate particles and how this acceleration and the observational properties change as we change some properties of the jet, or as we create a different medium, a more realistic one, a homogeneous one. These simulations are based on the work of Javi, who was a PhD student at MPIA, and also collaboration of Christian, my boss in MPIA, and Bhargav Vaidya from IIT Indore in India. These 3D GRMHD simulations, or jet propagating at parsec scales, have a nice resolution of 0.02 parsec, and Ravi implemented 3 different injection modes for the jet. First is a continuous jet, very traditional one that you can see the time evolution. This is a density map. Have the scale 4 parsec, and he also did some time-dependent jet that can be in bursts. We have this. You can see that it's a different propagation, and also he did a processing jet, which has a much different shape. We have a jet that is just processing. In this simulation, they are considering some Lagrangian particles that are injected into the jet, and with these particles, we can estimate the emission. For example, for Javi estimated the synchrotron emission. You have a synchrotron emission at 1 gigahertz for the continuous jet, which is different from the time-dependent jet, and especially different for the processing jet that we can see very nicely the movement. In calculating the SEG, we also have some different observational properties. These particles are accelerated by shock. This model takes into account synchrotron burst Compton losses. For Javi's work, it's only synchrotron. Here I'm just showing. This is my first simulation of this kind. We can see the density and velocity field, and here the normalization parameter and the magnetic field. We want to my next steps here is just implementing the inverse Compton emission and also the synchrotron self-Compton. In both. Mm-hmm. Okay. Mm-hmm. Yeah. Okay. Mm-hmm. Yeah. The particles are accelerated mostly in the internal shocks, but also in this border region. And here we have the total SEG. I'm just changing angles here. That's an angle of the line of sight. The main difference here is that for this precession, we have this plateau at 10 to 4 to 10 to 8, I think, gigahertz. But yeah, the synchrotron peak is the same. Maybe you can see more difference when I implement the inverse Compton emission, because this is pure synchrotron.
So we can postpone the questions because we are almost at the end of the slot.
Okay. Okay, just finishing. Synchromassive Compton, also something that I'm very interested in, more or less background medium, the same sense of the other two projects. We want to check if there's some redshift impact, especially for considering that the inverse Compton can interact with the CMB photons. And this is probably the biggest task, is implementing hadronic component. Right now, I'm doing this two step, just implementing this into a harvest model, but soon I will just test a more realistic background medium. I think I can finish here. So just thank you very much for your attention.
Thanks, Ivan. This is a beautiful work, and you have a lot of stuff going on there, huh?
Yeah.
Very nice. So now we have time for a couple of questions. Yeah, Betty.
Ivan, continue our discussion since last week. Yep. Very nice talk with the interesting results. I have a number of questions, so let me start with the feedback part.
Okay.
Because this is the one that you detailed more in this talk. So regarding the feedback, you got these solutions that, you know, the mass loss is entirely due to the AGN feedback, right?
Yes. Yeah. Because also our model, our initial condition is isolating the AGN. So there's only AGN that can do things. We are not considering stellar feedback for the model.
Yes, so my question goes in this line, because then you compared with observations, right? So the fact that you did not actually take into account the interstellar median evolution and the star formation rate, the dependence, right? Because you have this initial condition where you have all these clumps already, right? Yes. So this kind of simulation reminds me of those by Bicknell and his group in Australia, right? Where they have. On the other hand, in our work published last year with the PhD student, I mean, was the PhD thesis by William Eduardo. Yes, he finished, right? But that work, we actually did consider the formation of the clumpy interstellar median out of star formation, right? And then this makes a difference, because those clumps are not that, you know, you do not have very dense and cold clumps as in when you assume this initial condition. So life is more difficult in these systems. And then what we find, yes, thank you, because this introduction is necessary in order to make the comparison. This said, what we find is that the mass loading, so the m dot rate that you get to compare with the observations, is a lot influenced by the star formation driven wind, not only the AGN wind, because this provides the gross of the mass loading, which in turn is pushed by the AGN. So one injects power, velocity, and the other one provides mass loading. So the mass loss, that's why I said that this is very dependent on star formation rate as well, on the history, the evolution history of the multiphase interstellar median. So my question is, do you intend to compare both simulations and observations, because there are also this mass loading by different classes, Seyfert galaxies, ultraluminous, AGNs, all those classes, because they behave differently in the diagram of m dot versus mass, star formation rate, and time. So If you have then done this comparison, can you tell us something about this?
Okay. For now, for my models, I'm really isolated AGN, so I'm not taking into account any.
Right.
I'm aware of the importance of this stellar feedback. There's a lot of work and discussion what is the main mechanism. For this work in particular, we are comparing more since we are creating a lot of small clouds. I'm very focused on the very, very dense clouds. We are more interested in, for example, I'm working with Chris Harrison, he's an observational one, and he's very worried about tracking the right part of the outflow. For example, if I'm looking at O3 line, we track certain density.
Because the porosity is very high in your sense, in your simulations, right?
And we observe very high densities.
It's a lot of different.
So some lines of more than 10 to 4 centimeters per cube. And what exactly the part that we're tracking? This is I'm going to this line of comparison. There's a 10 to 43 errors per second AGN cannot produce the very, very dense clouds. So looking at O3 for this AGN is the same as looking for the more powerful one. So what is the best trace? What is not?
Right.
This is the line that we're doing this work. We're not comparing. Of course, we have a part of the discussion saying about stellar feedback and so on, but this is not.
One thing that's also important to take into account is that when you have the star formation and the supernova explosions, you have several hot superbubbles with cold shells that fragment. And these hot superbubbles, this changes completely the porosity, right? So it's a key point. But it would be interesting.
That's a lot of things to simulate together.
That's true. And another point, my last question regards to this last simulation that that I was because you said that you did not take into account the SED, the two peaks that you have is you said that is only synchrotron that are producing those two peaks.
Yes, it's only synchrotron.
So no inverse Compton here because generally, these two peaks, this one is synchrotron and the other one is inverse Compton. So
this is one of the results of Javi's work that I did not tell a lot about, but here we have the traditional synchrotron one, and here they found another synchrotron.
Wow!
Probably related to a much more energetic population of electrons. Like if you look to the spectrum and energy, to the high energy tail.
Right.
But this is only synchrotron.
Okay.
I think it's also very interesting because if I look to this, I would say, oh, synchrotron, inverse Compton.
Yep. It's curious.
Yeah, so we are a bit out of time. So there will be room for you. So as I said, Ivan is visiting us for the rest of the week, and so there will be plenty of time for discussions. And go find Ivan in room D311, and we can discuss more. He can discuss more his work. Let's thank the speaker again.
Thank you very much, people. Obrigadão. Tem muita coisa.